Swayam Prabha. Digital India. Educated India.
Our discussion on entropy as a property, and last time we discussed it with entropy as a function of temperature and volume, and now we will discuss another aspect, that is entropy. Entropy as a function of temperature and pressure. Since the appearance of pressure, you can imagine, you can anticipate that will make the presence of enthalpy felt in the system in the derivation. So there will be the derivative with respect to enthalpy and other things. So that will give us new relations. For that matter, we are actually considering this, the entropy as a function of temperature and pressure. So by definition, that is of a differential, this gives me ds equal to del S del T at constant pressure times dt plus del S del P at constant temperature times dt. So this is the basic definition, differential, as we start from the definition of an entropy as a function of temperature and pressure. Now we come back to first law, and the first law tells us that if we have a system which you put dq amount of heat, and that gives that raises the internal energy by an amount dE, and dW is the work done by the system. So that is the dW, and if it is reversible process, then I add dq reversible, and that is dE plus P dV here. And now from the second law tells us that dq Tds is basically dq reversible, because if dq reversible by T is the ds. So Tds equal to dE plus P dV is basically the combination of the combination of the first and second law. Now I express, since it is a function of T and P, it is often convenient to express this dE as in terms of H. So it is basically, we know that H is enthalpy is E plus PV. So dE is basically H minus PV plus P dV, and this gives me a dH, the differential, minus P dV minus V dP plus P dV. So that is my TdS, and you see that P dV gets cancelled out, and we have a simple relation T ds equal to dH minus V dP. Now again, we have gone from dE to dH, And now we again want to express it in terms of H is a function of H again is a function of temperature and pressure. Therefore, I can express it as del H del T at constant pressure times dt plus del H del P at constant temperature times dP minus V dP. So this gives me this. By definition, we have identified this as Cp. This is Cp dt plus del H del P minus V times dP, and that is T ds, or ds is equal to Cp by T times Tt plus 1 by T del H del P at constant temperature minus V dP. So this is my first relation 1, and this is my second relation. They are identical basically. So ds is expressed in terms of the increments in dt and dp. The same thing has been done here with some unknown coefficients here, del s del t and del s del p. So del s I can simply from 1 and 2, from 1 and 2 I can get the simple relation between del s del t at constant pressure, that is equal to Cp by T, Cp by T, and also there is another relation del S del P at constant temperature, that is equal to del S del P is 1 by T, that is del H del P at constant temperature minus V. So they are, say it is 3, say it is relation 4. Now we know these coefficients now. These coefficients are not something very abstract object, but they are related to Cp by T kind of thing. And now what I do, I will use the condition for an exact differential of differential of function of two variable. Then this I can differentiate this with respect to P and this with respect to T and see what we can get by equating them. So del square S del P del T is equal to 1 by T del of Cp del T, and that is equal to 1 by T del square H del T, P del P del T. So this is the quantity, because Cp is basically del H del P, del H del T kind of object. So this is the first relation. Another relation we derive del square S del T del P. Now see, it is del P del T and this is del T del P. This is equal to 1 by T times del square H del T del P minus del V del T at constant pressure, this quantity minus 1 by T square into del V del H del P at constant temperature minus P. Now you see that there are two quantities. This is a quantity, I can equate it, the cross coefficients are equal, and that leads to a condition that 1 by T del square H del T del P minus 1 by T del V del T at constant pressure minus 1 by T square del H del P at constant temperature minus V. So all the terms that I have written down for the right hand side of this equation, and this is this one, and that is equal to this side, the right hand side, 1 by T del square H del P del T. Now you see that the first terms, they get cancelled out, and if I multiplied both sides by T, I have a term that gives me del V del T at constant pressure equal to, both are minus, so there will be a minus sign here with 1 by T, and it is del H del P at constant temperature minus V. So this is a very interesting relation, that del V del T is now related to this particular quantity. So what is my del V del T? So this is 4, I say, I call it 5. Now from 5 and this one, 4, 5 and 4, from 4, 5 and 4, you can immediately see what is my del S del P at constant T, that is equal to this quantity, and this quantity has a minus sign. So I put the minus sign here. So it is minus of del V del T. This is another interesting relation that you can see, that is del S del V del T. So even if you look at it, look at this quantity del S del P, it looks like an abstract object, but this is a coefficient which is much more handy. That is how the this volume changes with temperature. Is a very simple relation, and so if you write it as if from my definition, that coefficient of thermal expansion alpha is, if you define it 1 by V times del V del T, then this gives me alpha into V is del V del T at constant pressure. So this is just an alpha minus alpha times V. So you can write it del S del V del P at constant temperature is minus del V del T at constant pressure, and that is equal to alpha minus alpha times V. So this is this quantity is nothing but thermal expansion coefficient with a negative sign and multiplied by the velocity the volume. So this is this quantity can be easily expressed in terms of the other properties of the system. And So this is fine. Now I can invert this relation 5. So from 5 and find out what it is. So it is basically, I put a minus sign here. So it is minus of t times del v del t del v del t, and that is equal to del h del p at constant temperature minus v. So if you put that minus sign here, this is T into del V del T at constant pressure, and this is the quantity. So this gives me a very, again, an important relation, del H del P at constant temperature, that is equal to minus T del V del T plus V. So again, this was the quantity that we could not understand what this quantity is, and to understand this quantity we had gone for a Joule-Thomson experiment, and we showed that this is somehow related to Cp, or specific heat at constant pressure, as well as with Joule-Thomson coefficient. So now you see that this quantity can be simply expressed in terms of the change of volume with temperature and at constant pressure. So basically, again, a thermal expansion coefficient kind of object. So this is another important relation. We may also call it another equation of state in terms of this enthalpy, an equation of state, a thermodynamic equation of state, since the right hand side is related to pressure, volume and temperature. Since the right hand side is related to pressure, volume, temperature. Another thermodynamic equation of state. So I may express this quantity in terms of thermal expansion coefficient also, but before that we revisit this particular exthermal, some expansion of a gas, that is Joule-Thomson expansion, which was basically an irreversible adiabatic expansion, that if you can remember. So we come back to that particular topic. So we revisit Joule-Thomson experiment, and you recall that this was basically an expansion process, an adiabatic, irreversible adiabatic expansion of a gas. So under this, what happens that, so there is a pressure drop, and as the pressure drops, the temperature drops, and there is a measure of this the temperature drop is Joule-Thomson coefficient. And we find that mu Jt, Joule-Thomson coefficient, is something like delta T delta P for under certain conditions, because Joule-Thomson experiment was done and it was shown that it is an isoenthalpic and enthalpic process. So it means its enthalpy is constant for the process. Enthalpy is remains constant. So it means delta H is equal to 0. So any change dH equal to Cp dt plus del H del P at constant temperature times dP. That was the thing. And for isoenthalpic process, for Joule-Thomson expansion, dH is equal to 0. So what we had, the Cp times delta T for finite process equal to minus of del H del P at constant temperature time delta P for finite process. And so this was the quantity. So I had del T del P for constant enthalpy H, and that is equal to minus 1 by Cp times del H del P at constant temperature. Now here comes the utility of this relation, and say it is 5, we call it 6, and let it be 7. So from 7, we can replace this by this quantity, and this is equal to minus 1 by Cp, and del H del T is V minus T into del V del T at constant pressure, this quantity. So V minus T into del V del T at constant pressure. So this is a simple relation for mu. So mu Jt is basically a relation of this kind, and if we just rearrange a bit, then this is equal to mu Jt, that is equal to minus 1 by Cp times V minus T into, now you need that, you know that V, that alpha, you write alpha equal to 1 by V del T at constant pressure, that is alpha. So T times, so alpha into V is basically, this is alpha, there is a T here, and you have del V del T, and this is alpha into V since alpha is this one. So this is, you can slightly rearrange it and write it as V by Cp times, I write it T alpha minus T alpha, I take the V out, here T alpha minus 1. So that is the final expression for mu Jt, Joule-Thomson coefficient. So Joule-Thomson coefficient is a measure of how much the drop in temperature as the pressure difference is created, or you lower the pressure. So it is volume divided by Cp and times T times the expansion coefficient. So, and you see that there is a provision for this coefficient which can make it negative. If, for example, if alpha T is greater than 1, which is for most of the substance, then mu T Jt is greater than 0, positive. And if alpha T is less than 1, then mu Jt is less than 0. That means it is negative quantity. So derivative, so in that case, when pressure drops, the temperature increases. There is an inversion, there is an inverted situation. So this case can be clearly understood when we can find out the expression for del H del P, this particular quantity. Once this quantity is known, that is thermodynamic equation of state is known, then we can find out explicitly the expression for the Joule-Thomson coefficient, and also explain the when this, at what temperature there will be an inversion of the Joule-Thomson effect. So the Joule-Thomson effect is something which depends also on the temperature of the gas at which there may be inversion. So the inversion of that temperature can be seen when it is when that temperature is something when it is greater than equal to 1 by alpha, or when it is less than 1 by alpha. So that shows that this is again a formal relation between different properties of a system. So whatever we do in thermodynamics, the final goal is to establish certain relation between properties. And you see that we started from the combination of the first law and the second law, and we worked out a typical process. We consider a typical irreversible adiabatic expansion where your enthalpy remains constant for the process, and we find that there is a drop in temperature because we change the pressure of the gas to very low, the low end. So what happens that in that case we can establish a relation between this coefficient to the other properties of the system. So volume is a property, Cp is a property, temperature is a property, and expansion coefficient of the gas is also another property. So so expansion coefficient actually depends on the nature of the gas itself. And so this relation, although is extremely general, but it is applicable mainly to gases because they are easy to handle. So that gives me a confidence that once you check it, the experimental relations, and they are if they are found to be okay, then we are satisfied that the entire formulation of the first and second law in its combination gives you the correct picture of a natural phenomena like Joule-Thomson coefficient, Joule-Thomson expansion. So that's fine. So with this, we conclude this particular part and go on the next topic for specific cases again for ideal gas and other things, and how to work out the entropy as such. So with this, I stop here and move for the next session. So thank you all for your attention.